¿Para abajo? Para abajo. Ah, ok. Ya sí.
On va commencer la session.
So we go on with the third section, the first one of the afternoon. We have a second talk, a mix between CFD people and GloBC people, if I'm not mistaken. Yeah, I'll go also. And we'll start with Julia.
Thank you. Hello, everyone. I am Julia Ruiz-Girona. I'm a PhD student at Lagos. And the title of my thesis is Projection of Regional Ocean Circulation Climate Change in the Eastern Pacific and Implications for Marine Associated Ecosystem Services. My supervisors are Véronique Garçon and Boris Avit. My thesis is part of the Situ Coast project. As we can see in this picture, the Situ Coast project studies the climate change in different regions that are the regions that we can see here. My study area is the yellow square here, which corresponds to the Humboldt system. More specifically, I'm focused on Peru and the northern part of Chile. So having this in mind, the research questions for my thesis are: how has climate change affected the Humboldt system so far? And how will climate change impact pressures on ecosystem services under different shared socioeconomic pathways? So the most important pressures and services in this area are warming, wave climates, upwelling, nutrient supply, the oxygenation and ocean acidification. And for services, CO2 uptake, carbon sequestration, primary production, mesopelagic production, fisheries, and agriculture. So in order to do this, we have this methodology. So the first point is to analyze in situ and satellite observations to assess mean state, trends, and variability. The figure we have here is an example of that. It corresponds to observations from the World Ocean Atlas in different domains in the Pacific to different depths, which corresponds to two different water masses. The area I'm mainly focused is the orange line, which is the southeastern Pacific. And as we can see everywhere in my region in the Pacific, the trend is positive, which means that it's warming. The next point is to perform future climate projections on Earth system models, then perform dynamical downscaling in order to obtain projections with regional models, and finally assess impacts on ecosystem services and communicate them to stakeholders. Finally, I'm going to show you some more recent results on CO2 response to Enso. So what this figure shows is during El Niño extreme events, we have the E index, which corresponds to the Eastern Pacific index, CO2 partial pressures anomalies. These data correspond to the sesame lens models to 35 different realizations. So what we have in the solid line is the ensemble mean, and the shading corresponds to the 25 and 75 percentile of the distribution. As we can see, during El Niño extreme events, CO2 concentration decreases, as we would expect since welling stops. However, we see that this reaction is stronger in Peru than in Chile, and this is because in Chile there's most likely this is because in Chile there's intermittent winds that still induce some upwelling. And so this is the end of my presentation, and thank you for your attention.
Thank you. So we go with the issue of global warming back to the issue of the source and the problem of decarbonization with Hector.
Good afternoon, everybody. My name is Hector Vargas, and today I will be presenting my PhD topic, which is high performance simulations of industrial gas turbines decarbonization through ammonia, hydrogen, methane mixtures. I'm doing this under the directions and supervision of Marianne Cuif, my supervisor on the industrial side, and Laurent Jiquel, David Herrera, and Elinor River on the academic side. What's the objective of my thesis? It's to decarbonize. Why do we need to decarbonize other than, saving the planet? It's because TotalEnergies announced 2 years ago that they want to achieve the net zero emission by 2050, which means we have to do it in like 25, 28 years, which is quite a challenge. How do we do it? In the context I work in is we achieve this by decarbonizing offshore, off-grid oil platforms. What do I mean by off-grid? So these platforms are mainly found in near the coast of Angola, and over there you don't have an electrical grid. So how do you produce enough power to extract the oil and the methane from the ocean floor? So you need the way you do this is to produce your own energy on site. And the way we do it right now is by burning methane in gas turbines. As we know, methane produces CO2. And one way to avoid this is by implementing the use of e-fuels like ammonia or hydrogen, and in particular, green or blue ammonia and hydrogen. Green being the ammonia ammonia or hydrogen that is produced by hydrolysis using renewable energy sources. And the blue one is obtained from methane by capturing CO2 and stocking it on the solid form. And if we have hydrogen, a lot of people work with hydrogen. Why do we choose ammonia? Well, because ammonia is easy to stock and transport. For hydrogen, we need to have cryogenic temperatures, and this means we need a lot more energy. And this is not the case for ammonia. For ammonia, you can have you can stock ammonia atmospheric temperature, atmospheric pressure, or you can have it at negative 25 degrees at 1 bar, or at 33 degrees at 18 bars. The slide is is wrong. You can switch the pressure from both tanks. And other reasons to have this is to use ammonia is that it's already in production. You use ammonia as a fertilizer in the agricultural sector, and also because it's also a fuel of interest for naval propulsion, which means we can transport the ammonia we will use on the platform and use it also to fuel the ships that will take it to our platforms. And how do we do it? We need to transition from methane to ammonia hydrogen mixtures. How do we do this? Well, first, one of the first challenges we face is that actually the literature on ammonia and hydrogen is scarce but very active. So there's papers coming out every 2 or 3 weeks, but we don't have a history. We don't. So we are setting the foundation in the last years. Another thing is that we need to choose a mixture, because as Jessica told us earlier today, you cannot burn ammonia by itself. It's not reactive enough. So you need to mix it with more reactive fuels like methane or hydrogen. So you have 2 options. You have already a fleet of turbines existing on the platforms, so you can either reuse them and adapt them, or you can redesign the whole turbine. If you decide to reuse the ones that exist already, you have 2 conditions. You have to reproduce the methane behavior, and you also need to have a mixture that's issued from cracking, NH3 cracking. So cracking is a procedure where you take a certain amount of ammonia and then you crack it and convert it into ammonia, hydrogen, and nitrogen mixture. When you want to retrofit your gas turbines, you have to take into account these two parameters. And if you redesign completely your turbines, you can get rid of the reproducing methane behavior constraint, but you need to pay the price to replace all the existing turbines. Another challenge we face is the emissions. With methane combustion, we already know we have CO2, but we have which we can call trace amounts of NO. And when using NH3 and H2, we increase the probability of having NO and NO2 in the combustion products. So you need to take care of it and to make sure that your configuration will not emit more NO than you're producing using methane. And another thing is that you cannot burn, as I said before, ammonia by itself, because the laminar flame speed and other characteristics are not adapted to burn by itself. So you need to mix it, and this will change also the behavior of the flames and the way you burn it. So now we know that ammonia cannot be burned by itself. So we have two main mixtures that we are studying right now. Both are produced by cracking ammonia and have similar behaviors to that of the methane combustion. My current objective is to implement a chemistry into our CFD LES code, which will be valid for several compositions, several pressure and initial pressure and temperature. And we will study the transport of the species and the reaction between them. And after validating the models, we will choose the one that's more adapted and that suits us better. And then we will reduce it. We will take the reactions that aren't that much important, that do not contribute to the combustion details we want to capture. And then we will introduce this reduced simplified scheme into our CFD LES simulations. After this, we will implement this chemistry and modify the existing turbulence combustion model to take into account our several multi-fuel case. And we will also analyze the conjugated heat transfer using the AVSP model solver. And in the end, we will end up with an adapter version of the AVVP solver and a demonstration of our model in a real configuration, which will be then used to by TotalEnergies to decide whether they want to keep their turbines and adapt them or buy a new one, or which is the most interesting mixture for them in terms of cost and combustion characteristics. And the first CFD LES simulations we've done are on a simplified bluff body burner, which we can see on the left side of the slide. And if you have any questions, we can discuss them at the end of this session. Thank you very much.
Thank you. So we now switch to William, and we talk about fire and atmosphere copy.
Okay, hello everyone. So my name is William Montolin. I'm a first-year student at GLOPSI team, and today I'm going to present you my topic entitled Improvement of the Representation of Living Fuel for Fire-Atmosphere Coupling. So this topic I'm doing under the supervision of Mélanie Rochoux and Patrick Lemoyne for CNRM. And today we are going to talk about fires, but not the same kind as you, CFD guy, but wildfires. So even though wildfires are part of nature, they can be deadly and destroying homes, wildlife, and polluting the air with harmful emissions. With an increase in temperature and droughts, they are becoming more and more worrying. So I showed you here as an example the area burnt between 2019 and 2021 by fire with a surface of more than 40,000 hectares, which we call the mega fires. So these events are out of control for firefighters, and predicting their spreading is not an easy task because there is such a complex and rich physics involved. Mainly, we are modeling this through the interplay between fire and atmosphere, where you have the fire heating up the atmosphere, giving rise to a strong convective flux. And while at the same time the fire is spreading at the ground at a certain speed, and this speed is depending on the surface wind from the atmosphere. So there is a lot of regimes existing depending on the fluid convective fluid number. You can have either a plume dominated fire or wind dominated fire. So by trying to recreate this complex physics, Blaze was developed by Aurélien Coste during his PhD for the fire parts. His model was then coupled with Meso-NH large eddy simulation for the atmospheric counterparts. And the coupled model Blaze Meso-NH was then compared to an experimental case and showed in particular two things. One was the importance due to atmospheric variability due to turbulence. And the second was the appearance of compressible effects at 10-meter resolution. So this was done for a non-homogeneous vegetation or fuel, if you want to say. And our goal during this thesis is to extend this case to a more complex vegetation, to have an even more realistic case. So to do that, first, we need to represent correctly the drag that the vegetation has on the fire spreading by representing the type of profile that the wind have. And secondly, you need to recreate behavior from the fuel depending on the characteristics of the vegetation. So with these two ideas combined, it will help us to evolve toward more real cases. So such as this one, which is the New Jersey case, with it's a pine forest with a very broad range of vegetation and a complex fuel. Thank you.
Okay. Attends. Okay, so maybe you can. No? On peut lui donner la main.
Rami, est-ce que tu pourrais te connecter?
Yes.
Tu lui donnes la main, pardon.
Vous m'entendez?
Oui, oui, on t'entend.
Ok.
Tu dois partager ton écran.
Voilà.
Ouais, c'est bon.
C'est bon?
Ok. Vous voyez mon écran, c'est bon?
Ça arrive.
Ça arrive. Oui. On voit le PowerPoint, du coup.
Ouais.
Voilà.
C'est bon là?
C'est bon.
Ok. Super. Okay, so hello everyone. I'm sorry I can't be here with you due to a COVID issue in my office today, but anyway, I'm going to present you what I've been doing since I started my PhD a few months ago. It began with a quite large problem, which was how to compute accurate LES of flows subjected to large-scale disparities while keeping a reasonable computational cost. To get started, we decided to explore the urban canopy problem before explaining why it's relevant for our big problem. I'll say a few words on how important it is to understand what's happening inside the canopy. More than half of the population lives in urban areas, and this number is expected to grow even more in the future. It is then crucial to understand the physics to evaluate its impact on the environment or to protect the population from release of pollutants, like we had in France near Rouen few years ago due to an industrial accident. It is then of interest to study in depth this boundary layer flow. Of course, it's related to a lot of different scales with features varying from 1 meter for the pedestrian or the cars to 10 meters for the trees, the housing, and even 100 meters for the corporate skyscrapers. This heterogeneous terrain gives birth to a complex wind pattern, which is very hard to predict due to the insane amount of parameters to take into account and obvious experimental difficulties, particularly in the roughness sublayer, where the flow is strongly influenced by the different features. To better understand such flow, we need numerical simulation. Large simulation proved to be well suited for such case, where the direct numerical simulation are too costly and the Reynolds average numerical simulation fail to extract the relevant features of such flow. We decided to explore the physics and validate our tools to begin with a basic, well-known, both experimentally and numerically case of an urban-like array using ELS2, an LAS incompressible solver from the Korea. As you can see, the flow is highly turbulent in the obstacle region, and the mean wind field is accurate with what we can find in the literature. Now that we know our tool is working well, we are focusing on finding the relevant variables which are influencing our flow. Of course, as you can see, the pattern of the array is one of them, but we can also think about the wind direction, the form of the obstacle, the density of the obstacle inside our domain, and I bet you can think about many other things. We aim in the PhD at taking advantage of such high variable space and complex flow pattern using neural networks and random geometry database to create a wall stress model of the roughness sublayer, and maybe later to extract the dynamics of the flow to provide accurate prediction of pollutant dispersion. Thank you for your attention. If you have any questions, feel free to contact me.
Thank you. We now go back to Mehdi. So we talk about wall modeling again.
Hello everyone, so my name is Emilio Concha. I'm a first year PhD student here in the CFD team, and my topic is wall modeling for large simulations of triple flows. So a bit of context. So I'm dealing with large simulations in which we need to simulate the largest and most energetic structures of the flow. However, one limitation is that when you are nearing the walls of walls, it calls for the structures you need to resolve are smaller and smaller. So it calls for a fine enough mesh, and it means a high computational cost. And one way to avoid it is to use wall models that will model for you the fluxes at the wall. Then you need you can compute on a coarser mesh, and it avoids a lot of pain for you. However, the challenge we have is that here at CERFACS, we want to model quite complex flows, such as turbulation flows, and there are complex phenomena at stake. For example, there is pressure gradient in the boundary layers. Also, they can have shock wall interactions and boundary layer transitions, and most of the phenomena are also non-stationary. And one contradiction is that the most widely used wall law is based on the classical and historical log law, which relies on restrictive hypotheses, such as Panhard problem, stationary flow, and pressure gradient. However, it is quite efficient to compute with that flow, so it's still used. But the whole idea of my PhD is to try and improve this law in our solver AVDP and we hope to have better predictions for our turbo machinery flows with that. So what I did up to now is I implemented in AVDP the thin boundary layer equation model, which relies on solving an ordinary differential equation in the first cell of the mesh. And it has a pressure gradient embedded in it. And for now, I tested it on the turbulent channel just to know if it was behaving as we wanted it to in a controlled environment. And that's the case. And the work in progress is trying to test the TBLE model on a diffuser case or other cases where the pressure gradient is known to have an effect on the flow. And also, I'm trying to see if other wall models can be considered, especially trying to include the non-stationary effects in the models to better couple the LES framework with the wall models, which are based on the Ron's equations now. So that's all for my talk, and if you have any questions, you can ask them.
Next speaker is Rashid, and you will be talking about hybrid physics, AI approach for cloud cover.
Je peux vérifier si tu as fermé ton micro.
Normalement, c'est fermé.
Non, on t'entend très bien, donc c'est pas fermé.
Oui, je l'ai activé pour le dire.
So, hello everyone. My name is Rashid Elmontosir, and my PhD subject is hybrid physics AI approach for cloud cavernous clustering, and I'm supervised by Olivier Pincourt and Corentin Lapayette. So, the idea of cloud cavernous clustering is given the last observations, like to predict the next cloud states. Oh, it's not, it's an animation. Anyway, it's actually animation, but anyway. And here in the right, we have satellite observations, ground truth. In the middle, we have unit prediction. In the right side, we have XM's product. I don't know why it's not working, but no. The problem with we have XM's results here are quite good, but the computation time of XM is around 20 minutes. But this model uses atmospheric motion vectors. On the other hand, the unit is actually quite fast, but the problem is the small structures tend to disappear over time. So this unit doesn't take advantage of any physical knowledge. So the idea of our project is modeling a deep learning architecture that take into account physical knowledge, PDEs in, for example, PDEs to take it into account, for example, the transport of clouds by winds. Our first architecture is the following one. Here we use a transport equation. As you know, to solve the transport equation, we need velocity, the velocity field. So we introduce a unit upstream. That unit takes as an input the last two observations, and we get as an output U in V, We solve this equation using an ECAFO multiple times to get a sequence of the next states. This forms the deep learning architecture trainable, and we have trained this architecture, and we came with these results. It was a GEF actually. Anyway, the problem is that these results are this model is trainable, and we actually show something in the GFs. So the results are quite good, and actually we should have here a velocity field from the T0, which we'll see a velocity field that deduced from the just two observations. We estimated a very accurate velocity to transport the clouds over a period of time, for example, 2 hours, 3 hours. It's a non-custom problem. Thank you.
Okay, I guess. Do you have a poster session or?
No.
No, but for the people interested, I guess you have to sit with him and look at the movies. So the next and final talk for this session is Riwan, right? That's how you pronounce it. So it's a control of laminar transition.
Hi everyone, I'm Riwan Amashi and I'm leading to a lower parietal friction and a lower speed to wall heat transfer. So the industrial interests of this topic are the reduction of fuel consumption, especially for the civil aviation, and the reduction of the thermal protection constraints for future hypersonic aircraft. The natural transition of a boundary layer consists in the linear development of primary instabilities until certain amplitudes, past which nonlinear interaction become predominant. The so-called secondary instabilities then lead to the breakdown to turbulence. That's to say the apparition of turbulence spots that grow and multiply until the boundary layer becomes fully turbulent. Consequently, the attenuation of these primary instabilities can allow us to delay the transition. To achieve this attenuation in the subsonic regime, we can use the suction through a perforated wall. This will make the boundary layer profile fuller and less prone to destabilize the Tolmien-Schlichting waves in this flow regime. For hypersonic regime, it's different. The second Mach mode is the dominant disturbance that can make the boundary layer turbulent. This disturbance represents high frequency trapped acoustic wave within the boundary layer. So the resonant nature of these instabilities is sustained by the wall acoustic impedance. So covering the wall by porous coating can allow us to delay the transition by attenuate the Mach second mode by absorbing the acoustic energy. So the objectives of this thesis is to study the modal model and nonlinear amplification of instabilities within subsonic and hypersonic boundary layers by performing GNS with Jaguar. Then we want to assess the effect of control systems on the development of instabilities by modeling the effect of porous walls with temporal impedance boundary condition, and eventually couple this boundary condition with a wall suction for subsonic cases. And then we want to improve the performance of control systems by using our optimization algorithms to evaluate the properties of especially inhomogeneous porous materials. Thanks for your attention.
Thank you. Time for the break. So initially 25 minutes break. We're a little bit late, so it will be 20 minutes. And give you the next rendezvous for session 4, which starts at 3 here in the same room. Enjoy the break.
So this is the last session of this day. Before the awards, just after this session. So don't forget to vote if for the posters, because this session for the presentation there is no poster associated to the presentation, and so we have 8 presentations for this session. The first one is I hope I will not have some problem with the name, but it's Sriram Sankuran Tripathi. Yes, thank you. It's correct first name.
That's correct.
Oh, say thank you. So yeah, the title of your PhD is High Fidelity Simulations to Study the Propagation of Airborne Viruses in Closed Environments. Thank you.
Good afternoon, everyone. My name is Sriram Sankaran Tripathi, and my PhD thesis is study of propagation of the airborne viruses in closed environments using high fidelity simulations. And I'm a first year researcher, and my supervisors are Florent Duchesne, Nicolas Audier, and Thierry Poisson. And this is in collaboration with Valeo. So before I start the presentation, I would like to say thank you for all the people who worked in the scientific community and also who are frontline workers during the COVID time, which made our lives easier. And I already know that we all hate COVID here, and because it takes one complete year from us, 2020. So don't worry, I will avenge for you all, which makes, by definition, I'm an avenger. Yeah. Okay. So we get right into the topic. So many of you, I don't know if you know that the first COVID case, as per the officials, was discovered on 31st December. And since then, we had a pandemic over the entire world, and we had like a total of 6.3 million deaths, kind of considering the current situation. And if you look at only France, you have 145,000 deaths. And this is something very sad, because we have a World Health Organization, and hopefully we should have come up with a better scenario in the end. But what did World Health Organization do is, if you know, after the first 4 months, they have given us the official guidelines, which is like mandatory wear a mask, maintain social distance. If that not works, go for lockdowns, and and then it worked for some time. Then we had a Delta wave, and again it repeated. So, and then they come up with the first vaccination validation right after 11 months. And 11 months, you see already how many people have died. So why did this happen? Well, the idea is this is the first time we had a pandemic with an airborne virus? Not exactly, because we had some of the airborne viruses in the previous history which are catastrophic in the mankind. So such as like the rhinovirus, influenza, and human SARS, etc. But and there are actually studies on these. Despite having studies, we still came up with this current situation. Then what is the problem? The problem is that the World Health Organization, actually the entire world, reacted to the situation. They did not come up with a proactive approach based on the previous history. And the proactive approach is basically come up with a way to prevent this virus propagation already. And in order to do this, we need to know how airborne viruses propagate. First thing, I mean, they propagate basically in 2 variations, which is a direct exposure or indirect transmission. And in this PhD, we are talking more about the indirect transmission between infected human and non-infected human. And in order to do this, we have to do a detailed study on the respiratory droplets, and also a detailed study on the environmental effects. So let's get into it. So did you know if, for example, if I suddenly cough, or if I sneeze, the droplets that I emit will have a speed of 5 to 20 meters per second. And with the correct weather conditions, it can travel up to a distance of 20 feet. So basically, you all will be infected. And the size of these microns are also like ranging from 0.1 microns to 1,000 microns. So we are mainly focusing on the microns which are suspended in the air. And this lifetime of these suspended aerosols in in air is approximately 2 hours, which is scary. But when you consider them, when they got attached on the surface, they stay alive for a very long time. And the second thing, which is an important factor, is the environmental effects, such as wind speed, turbulent dispersion, temperature, and humidity. Because if we are outdoors and we have a wind speed of 5 km/h, example, my sneeze or something, it can travel up to 6 meters. And what did World Health Organization suggest is 1 meter. So it's not at all okay. And turbulence dispersion is very important. For example, if you consider this room, there are so many obstacles, and when I speak, the flow field inside this is manipulated because of these obstacles, and therefore the particles which are carried by the turbulence, they also get separated. So if I just cough in this direction, it doesn't mean that the droplets are only here. It'll travel in the entire room. So that's not good. And temperature and humidity also play an important role when it comes to evaporation effects of these droplets. So this is also something that needs to be considered. And hence, the entire studies that have been done in COVID or any airborne viruses can be divided into 2 parts: indoors and outdoors. And we will be working only on the indoors. And we have a paper, we have many works on this, and one such work is by Florent Duchesne with Valeo. And he has simulated how the droplets travel from an individual when he is placed in different positions, and how they propagate throughout an entire bus. So with this, I would like to say the objective of this PhD is we have to come up with a mitigation solution in order to make sure that we can prevent this propagation inside a public transport like a bus, for example. So in order to do that, we collaborated with Valeo, who provide a UV Purifier Design, which is the solution we are using in order to prevent the propagation. And you might wonder why we are going with UV, and it's basically because we already have UVC radiation, which is also known as germicidal radiation, and it can kill COVID. There are studies on that already that it can kill COVID. And with this, I can show you, this is the purifier that I've been working on. Over here, you see these 2 bulbs. These are the UV cylindrical UV bulbs. Over here is the inlet fans and the outlet fans, which extract the air from the outside and send it back. And this is just an inlet and outlet plenum, as you can see. And here, this is a mesh. And here I can tell you that if I want to find out the efficiency of the UV purifier, I need to do a high fidelity simulation, which takes care of all the phenomena that I just spoke before. So I need to understand the flow field inside the purifier. I need to understand, I need to inject the particles and track the particles. I need to add a fan model because we have inlet fans. So the spiral motion that comes out through it needs to be considered. And also a radiation solver because we are using a UV purifier, UV bulbs. So with this, I first started with LES simulation over inside the UV purifier with only a constant velocity flow. So it doesn't have the fan model in it. And this is the instantaneous velocity profiles. And after this, I've also did a time average velocity profile also. As you can see here, this is how it propagates. So I have to work in different domains at once in order to couple them in the end. So this is one thing. And the other thing that I've currently worked on is on a radiation model. I need to know how to use a radiation model when it is about to be coupled with a flow field. So first, I want to know how a radiation model works. So we created a radiation model using bibliography, and also we have a Prisma solver here at CERFACS. So we use the Prisma solver, and we just took a simpler geometry like a domain with 2 cylinders, and in that we have seen how the irradiance is, and as you can see, they almost have similar results. Particularly the graph where the line is passing between passing through 2 cylinders, the results are matching, but there are small issues where I need to work on the Prisma simulation, because as you can see, it is not averaged azimuthally in its direction. So With this, I would like to say that the work I'm basically doing is I will I'll finish this radiation model. I'm currently already running LES coupled with a fan model, and we will be running with a Lagrangian model. We'll combine all this. We will run inside a purifier, and we will see how efficiently we can kill the virus. And then we do this entire thing by installing these purifiers on the inside the bus, and we will see how we are preventing it and how it is a mitigation solution. And with this, I conclude. Thank you.
Thank you. So, sorry, Marcus.
Nathanael?
Yes.
So the second speaker is Nathanael Rouland, and the topic is modelization and simulation of enriched hydrogen turbulent flames. So up to you, Nathanael.
Okay. Is everybody seeing my screen? It's good?
Yes, but yes.
Yes, everything.
No.
No, change the screen.
Ah. Uh-huh.
That's right.
That's okay.
Good?
Yes.
Okay. Yes. So hi everyone. Sorry not to be here. In fact, the reason is directly related about what we've just heard. I'm Nathanael Roland. I'm a first-year PhD student in the CFD team, and I will introduce you my PhD topic, which is simulation and modeling of turbulent flames enriched with hydrogen, supervised by Benedict and Eleanor Weber. So, well, why do we want to burn hydrogen as pure fuel or mixed with other fuels? I'm not the first one to say it today, and I would probably not be the last, but we are in serious trouble. The IPCC is categorical. We have to drastically reduce our green gas emissions. In particular, in the aviation, even if the simpler way to produce less greenhouse gases is to not use aircrafts. But if we want to keep flying, we have to learn how to fly without fossil fuel. In that way, if we don't consider all the matter about how to produce it in a clean way, how to store it, etc., hydrogen combustion might be one of the solutions. But new fuel in aircraft engines meets new challenges. Among so many others, this thesis focuses on 3 of them. So first, the high flammability and the high diffusive nature of hydrogen lead to produce more flames in diffusion regime. So we have to improve models on that topic. Secondly, in hydrogen mixture, we can observe high effect of preferential diffusion and high effect of composition on the gas viscosity and species diffusion. In that way, transport modeling becomes crucial, much more than with fossil fuels. And finally, the higher temperature flames lead to higher NOx emissions, and we have to be able to predict those emissions. Okay, so during the past first months, I focused on transport phenomena modeling, more especially how to integrate molecular theory of gases in the calculation of transport properties in our code. So to do that, we use mixing law for viscosity and for species diffusion, and the expression of pure viscosities and binary diffusion coefficients are derived from the kinetic theory of gases. Those formulations allow us to take into account the composition, influence, and the preferential diffusion phenomenon. And this will be available in AVBP in the next month. So for instance, you can see on the left, some plots show the difference between the current evaluation of viscosity in red and the complex one in blue for different mixtures. So in order to test the different models, I will mainly study 2 cases. So the first one is a slot burner configuration, where you inject the reactant in the center and the products on each side. And the second one will be the hydrogen injector, who is currently developed at YMFT. Okay, thank you for your attention.
So the third speaker is Marcus Holzer, and the topic is code generation in a lattice-Boltzmann framework for exascale computation.
So hello everyone, my name is Marcus Holzer. I'm a first-year PhD student, and my topic is code generation in the Boltzmann framework for exascale computing. The work is together with CERFACS and FAU. And basically the problem I'm facing is that supercomputers nowadays become more and more complex and also more heterogeneous. So basically we have a problem with performance portability, which is a major target for modern HPC systems. So by looking at the top tier supercomputers at the moment, we have, for example, the Frontier supercomputer, which is powered by AMD GPUs, while then other computers have ARM architecture or NVIDIA GPUs. And to make use of this, we approach a code generation approach, which leads to a separation of concerns, or which is the idea is to have a separation of concerns between model development, that the model development can be done in a DSL-like structure, so separated from the actual optimization, which is then done in the second stage, and then the hardware-specific code is generated, which runs on defined specific on the hardware, which should be utilized in the simulation. And the code that is generated is for the Boltzmann method. So we have heard it before that how the method works and coarsely. So I don't talk about this in detail now, but yeah, that's the idea. And the application from this for the outcomes should be consisting of different complex problems. So we see, for example, here multi-phase flows with high density ratios. Here is the problem, of course, that we need adaptive mesh refinement to capture the interface, which is moving there. Then we have body fitted, we have boundary conditions that need to be fitted to the geometry, which is a complicated scenario or it's complicated in many simulations when using Cartesian grids. And what is important also is a combination of lattice Boltzmann finite difference and finite volume. So for example, in the blood flow simulation, or in the blood flow in the arterials, we have models that are used with that use finite volumes to resolve the non-Newtonian flow, and this should also work for large scale and combination with the ABM incorporated. And the first results, which I can show for now, are conducted with multi-phase flows on the former #1 supercomputer in which is on the large supercomputer for now, the Schultz booster system in Jülich, and this is conducted on the A100 GPUs. And what we can see here is this is a configuration with uniform meshes, so not adaptive mesh refinement so far, but we can still see that with communication hiding strategies and overlapping of computation and communication, we achieve a near perfect scalability. And what is also noted here is that we not only try to get performance advancements or things like that, but we also always compare with theoretical peak performance limited, which we evaluate before actually benchmarking the model, and then from this theoretical approximate or assumptions, we try to gather this and compare with the gains benchmarking simulations, and this leads us to the first promising results. Thank you very much. And
so the next speaker is Nicolas de Tomaso, and the topic is LES simulation of constant volume combustion.
Hello, everyone. I'm Nicola. I'm second year PhD student in the CFD team at CERFACS, and I work on larger dissimulation of constant volume combustion. This project is framed in the INSPIRE ETN project, which is an European Marie Curie project. So as we all know, a classical gas turbine cycle has undergone no major changes in the last decades. So the most important efficiency improvement have been done in terms of cooling, in terms of overall pressure ratio and the peak of temperature. So a technological breakthrough may be needed in order to change the thermodynamic cycle. And at this point, the pressure gain combustion comes into the picture. Basically, constant volume combustion is a concept of pressure gain combustion. And in particular, it is a pretty good solution because it does not involve any particular issues such as shock waves. And it is characterized by an ideal thermodynamic cycle, which is higher than the one of the Bragg cycle. Of course, this kind of solution has some drawbacks. For example, unlike piston engine, there is no piston that reduces the turbulence level inside the chamber. And the spark ignition for this reason is strongly affected by turbulence. In particular, this kind of combustion chambers are quite challenging from a numerical point of view. Here, just an idea of the overview of the combustion chamber that I'm computing in this moment. This chamber has been already investigated from an experimental point of view at the Purifier lab in Poitiers. Here you can see, for example, an intake pipe and exhaust pipe and the central volume where 4 nozzles let the fuel enter the chamber. Here you can see, for example, the pressure signal inside the chamber, which divided, we can say, each cycle in 4 different parts. An admission part, number 1, where air and fuel are injected inside the chamber. A combustion phase, which occurs at constant volume. An isochoric cooling phase, where the pressure and temperature goes down. And then an exhaust phase where burnt gases are released outside the chamber. So in the first part of my PhD, we have built a numerical approach using the code AVBP in order to simulate with a certain fidelity the 3 main phases of each cycle. Here you can see, for example, the admission phase, the combustion phase, and the exhaust phase. In particular, we have built and introduced in the code novel boundary conditions in order to mimic the effect of the wave. We have built a chemical scheme that works high pressure conditions. We have coupled the energy deposition model to use for spark ignition simulation with the TFLES, and we have enabled the TFLES to work with the variable fresh gas conditions. Basically, the numerical approach has given good results in terms of cold flow here on the left, in terms of the overall cycle on the right. Here you can see the reproduction of the pressure signal obtained with AVBP for the 3 phases. In blue, the admission phase, in red, the combustion phase, and in black, the exhaust phase. Next step is to analyze cycle-to-cycle variations. So the idea is to chain multiple cycles and verify if the code and LES approach is able to evaluate the link and the effects of one cycle to another. Thanks for your attention.
So the next speaker is Olivier Coudre. And the topic is accounting for correlated observation error in variational aviation data, assimilation, and the implication to wide swath altimeter data.
Thank you. So I'm just going to present quickly what that assimilation is, though you already heard a lot about it today. So basically, in its most basic setting, it's just about combining all the information that we have to estimate the state of a system. So say you want to estimate the temperature in a room, to see in front of the camera. So basically, you could have some a priori guess, some information. For example, you know there's some heat on one side and another door on the other side. So you have a background state which is basically everything you can guess before. So if you're doing a weather forecast, for example, it could be a previous forecast or some climatology. And then to be more precise, you have some observations which are scarce and also usually riddled with error. So you have errors on the background, errors on the observations, and you want to determine the best compromise, which is the analysis. And basically the way to do that is to characterize statistically this error. So through covariance matrices and a lot of assumptions. And basically once you do that, you can really determine the best statistical compromise, which is the analysis. Because to do so, you need to characterize your errors properly. And what happens in practice is that beyond what's cool in theory, you have to do some practical code. And when we are working on these systems, these are huge systems. For example, you want to represent the state of the atmosphere or the ocean everywhere on a quite precise grid. So basically, you have systems the size of billion variables often. So you can do everything you want, and especially it's more convenient. You need to have an access to the inverse of the covariance matrix of the observation error. So basically, you have this covariance matrix, which is always taken diagonal in practice, because if it's diagonal, it's easy to invert and it's cheap. But it does imply some wrong assumptions, because basically, if you have this matrix diagonal, you assume that all your observation errors are uncorrelated. And what happens when you do that? That basically you said my error is white noise. So in a spectral space, it's just constant, the same everywhere. And this is not true, because in practice, usually with high resolution measurements such as satellite data, if you do a mistake at some point, probably the next observation is wrong as well. And so you would expect this kind of spectrum from the real data. So what we are doing right now is trying to get this more accurate representation using some numerical tools which allow us to approximate the inverse of some operators at a cheap cost. And basically, the tools are based on diffusion. And our current application is wide swath altimetry. So it's a SWAT mission, which will be launched quite soon, actually, which scan basically the surface of the ocean of the land to get some elevation measurements. And basically, what we see here is a sample of the correlation estimated from simulated data. And if it was white noise and appropriate to assimilate it with uncorrelated error, basically what you would see is just a red dot here when it comes to correlation and nothing else. And basically, you can see here that there are significant correlations up to 2,000 kilometers away. So this assumption is very wrong in practice, and we know for sure that we won't be able to assimilate this data in the current system without some improvements. So the goal of this PhD is really to use some finite element model approximation to approximate its inverse at a low cost and figure out what happens next, because data estimation systems are really large and everything interacts with everything. And so the purpose is really to figure out what will happen and if we can make it work. Thank you.
Thank you. The next speaker is Alexandre Coudre, and the topic is modeling and simulation of sustainable aviation fuel combustion, including soot production in aeronautic engine conditions.
Yes. Thank you, everyone. My name is Alexandre Coudre, and this is my PhD thesis about the SAF and their pollutant emissions. So a few words about SAF. One SAF in particular, this is the ATG SPK, which stands for alcohol to jet synthetic paraffinic kerosene. If you blend it with conventional jet fuel or aromatics, it is a drop-in fuel. That means you don't need a modification in the airplane or the infrastructure to fly an airplane. And without aromatics, you need a slight modification for seals, and you end up with less soot precursors because aromatics are soot precursors. It is synthesized from crops such as corn and sugarcane, so you should end up with less CO and CO2 emissions. Because it is synthesized from a well-known process, this fuel has a better non-composition than conventional kerosene, so it is easier to model. Yet you can still have some soot precursors arising from few pyrolysis, and you need to quantify the soot volume fraction and the particle size distribution, which means you want an accurate gaseous phase description and accurate soot models. A few words about polycyclic aromatic hydrocarbons, PAH, which are precursors. They arise from pyrolysis product to form the first aromatic ring, benzene, and through a mechanism of pH growth, you end up with a much heavier, much larger pH, and all All of this is described with kinetics models, which generally involves a lot of species you need to transport. Then you got soot models to describe the nucleation, the surface growth, and the oxidation of a soot particle. First methodology to describe the pH you want to have to describe soot is the full reduction of an arc. So this one is done targeting pyrene, the soot precursor we are targeting, in aeronautical engine conditions. The reduction is performed with arcane and soot calculation with Canberra soot. So here are two interesting quantities for soot production. And you can see that the reduced mechanism in red is in good agreement with the detailed mechanism in black for a wide range of equivalence ratio, but you end up with 33 transported species. So next on the pH plate, we need additional strategies to describe the gaseous phase, such as the pathway lumping of pH growth. This is something we presented at ECNC in San Diego. The pH tabulation and two-step and arc chemistry, something a bit like Nomagete. And we ask ourselves, is a pyrene suitable for the species used for dimerization? And next, soot models and TFLS and multi-component fuels, basically sensors. Thank you.
Thank you. So the next speaker is Suzanne Salle, and the topic is the impact of climate change on aviation.
Good morning, everyone. So I will present to you my subject, which is the impact of global warming on aviation, and more specifically on the performance of aircraft engines during takeoff. So this is my first year of PhD. I am under the direction of Sophie Ricci here at CERFACS and Nicolas Gourdin at Isae Supaero, and also under the supervision of Emilia Sanchez at CERFACS also. So to give you a bit of context, aviation contributes to global warming, both by CO2 emission and non-CO2 effects. And this subject is focusing on the inverse problem, which is the global warming effects on aircraft performance. And more specifically, the rise of atmospheric temperature and humidity and how it affects performance of the airplane. A simple example would be the rise of temperature gives a lower air density and so a lower lift force. But here in this project, I focus mainly on the effects on the performance of the engine itself. So the main objectives of my PhD are to quantify the impact of atmospheric variables and their uncertainties during the next decades, so until the end of the century, on the engine performance of the aircraft during the takeoff phase. So this is done through three main axes, let's say. So first of all, the modeling of future atmospheric variables, which is done through climate models. And I take the outputs of these climate models as inputs of my study. So here it's temperature and humidity. Then the construction of an off-design aircraft model that is supposed to give as an output something to represent the performance of the engine and of the aircraft. So here what is used is the maximum takeoff weight, MTOW, which is the maximum weight at which the aircraft can take off in good conditions. And it's supposed to represent how the performance are affected by the rise of temperature and humidity. The last part of the subject is the uncertainty propagation and sensitivity analysis, because atmospheric variables in the future are submitted to a lot of uncertainty. We don't know how to exactly predict what's going to happen. And so it's important to conduct a sensitivity analysis in order to ask which of the input variables are more impactful on the sensitivity of the output. So these slides describe the methodology a bit more, but I think I don't have time to go too much into detail into it, actually. So I'm going to present to you more the main results that I have right now, which is this map that represents the percentage of days on which the MTO must be reduced by at least 5% of its original weight. So for two different future periods of time. So in yellow, you have from 2020 to 2050, and in orange, you have from 2070 to the end of the century. And this is according to data coming from the scenario SSP 585, which is sort of the business as usual scenario. We could say it's the most pessimistic scenario about the future of our carbon emissions. So what we can take from this map, first of all, is that the results are heterogeneous depending on the geography. This is due to the importance of local climates. We can see that some cities are actually already affected by days where the heat imposes restrictions on the takeoff weight, such as Mexico, Johannesburg, and Sao Paulo. And we can also see that we can expect a rise in the number of days with restrictions on the takeoff weight in time, which is logical because of global warming situation. So in conclusion, so the MTO is affected and the aircraft performance is affected by the rise of temperature and humidity. And where I am in my PhD right now is that the methodology and the workflow is basically done, also thanks to 3 different master internships that were done before me in this project. And now my main objective is to improve each module of the workflow. So for the simulation of the aircraft, it is now based on a 0D model of the engine, which is very low fidelity. And my aim is to kind of improve this model so that it represents something closer to reality. Still being some 0D simulation, because with sensitivity analysis, you have to do a lot of computations. But the idea is to kind of simulate some aerodynamical effects that are occurring inside the engine. Also, concerning the climate data that I use, I'm only now using the output of one single climate model. And the idea would be to do a multi-model approach in order to compare different simulations of climate and reduce the uncertainties on that. Last but not least, for the uncertainty quantification part, some work has to be done still in order to determine how to assess the importance of each variable, considering that these atmospheric variables have some amount of dependency between them, which is something that is quite tricky to take into account in sensitivity analysis. So those are my objectives for now. Thank you for your attention.
And so the last speaker of the day is Emilio Concha, and the topic is it's not the same. It's approximately the same. So dynamics of Chile, El Nino.
Okay. Hi everyone, my name is Emilio Concha. I'm doing my PhD between CERFACS and the Laboratoire de l'Aéro. So the topic of my thesis, as you said, it's a different title. So the topic of my thesis are the dominant modes of climate variability at mid-latitudes. Nonetheless, in the process of studying them, we found another climate mode that's called El Niño that's closely related to them. So this talk is focused on that. So here I show you a map of sea surface temperature variability for all the globe. And of course, you can see the one that stands out immediately is the El Niño Southern Oscillation pattern. Nonetheless, there are other places in Western coast that also have a high variability in temperature. And this variability is dominated by air-sea coupled climate modes that have a feedback that's the feedback through which they work, it's very similar to the one from El Niño Southern Oscillation. So they have been named after coastal Niños and Niñas. So because of the location of these modes in upwelling coastal areas where we have like water that comes up with a lot of nutrients, they can have important impacts of ecological or socioeconomical type. So as I said, we're focused on one of these modes. You can see there are 5. The last one that has been most recently described is Chile El Niño off the coast of Chile. So here you can see very well the pattern of El Niño because it's overshadowed by the big variability of Enso. So here I show you the spatial pattern of Chile El Niño that we calculated by previously removing the variability from Enso, and also the time series of this pattern where important events have been highlighted. So what we see here in the figure is those are the arrows are wind anomalies. So we have debilitated winds that generate a warm anomaly of surface temperature of the coast of Chile to modify the upwelling processes. So our objectives are to investigate the trigger mechanisms behind Chile El Niño and also to study its sensibility to future climate scenarios under different conditions. So to do this, we want to use models from the SEMI project. And to start, we evaluate how these models reproduce Chile El Niño events. So we do this, by performing a composite analysis. So here we have results for observations and for an ensemble of 42 SEMI6 models from historical runs. And we perform this composite in 2 zonal sections at 25 and 35 degrees. So I hear the y-axis, it's time. So 12 months prior to the peak of the event and the 12 posterior months, and the y-axis is degrees of longitude. So in short, you can see that SEMI is able to reproduce the magnitude, the duration of the events, and also the location with respect to the coast. So despite the lower resolution that this model had, and also the lack of realism in its in reproducing upwelling dynamics, they're quite skillful at reproducing Chile El Niño events. So we think they will be a useful tool to study this type of events. Thank you for your time.
Thank you. At the end of this session, and we have next event is the best poster and the result of the vote. So I have to wait for the result from Brigitte.
Now it's time for you to go vote online for the best poster. And in 20 minutes, we'll
So it is.
we'll be back with the results.
So at 4. So go back at 4.
Yeah.
Okay.
So you can stay here or maybe grab a coffee or
And there is some suspense for the awards.
Yeah.
Best poster.
Go vote if you haven't done it, and we'll see here again at 4 p.m.
Oh, no, sorry. I have the result.
Vote?
No? So,
Donc on a dit à 4 heures.
Ah. Así que yo conservador. No, no, pero tenía, había hecho, me puede estar al menos cuatro tenía.
Tenía cafeína para contrarrestar un poco de cafeína y aún así de en España, ¿cuál es? Aquí ya está. ¿Te acuerdas la manifestación? Yo me quedo claro. Incluso yo la aprendía porque vienen yo creo que la potencia la religión
So thank you a lot. So the winner is, so first for the presentation of the PhD in 3 minutes. So the winner is Jérôme Dabas.
Okay.
So the award is a pass for 1 year. It's not a 1 day, but it's a pass for 1 year for the stateless pass.
Thank you very much.
And for the best poster, the winner is Thibaut Gilliou. It's the same. Wow. Thank you a lot. So I hope we will have a lot of candidates for the PhD in 3 minutes for next year, and I would like to visit, because there is a lot of organization behind this day, and also to Clément and Victor because there is also a lot of time spent in order to organize this. So thank you a lot for all of you. And we'd like to make a picture just outside in order to have some souvenir of this day. So thank you a lot.
Thank you very much all for coming, and we'll be stopping the transmission right now. Bye.